Okay, do we got any questions on anything? We're doing all right here so far? Coming up. Sounds good. So we're off to the next one here. And the next one is doing projections. So what we're doing is we're projecting a force onto a line. Okay, and in 3D that gets a little bit complicated. So we use this mathematical tool called a dot product to do this. Now you'll cover this thing in Math 254. If you don't take Math 254, we're covering it here. And what you do, you just, to do a dot product, you multiply the like components of vectors together, and then you add up the products. When you do a dot product, what you get out of it is a scalar. That's what you get out of doing a dot product. So you just take ax bx plus ay by plus az bz and add them up. And it just so happens that when you do that, what you get is the product of the two vectors times the cosine of the angle in between. So if you take the line vector, which would be a position vector, r, if you do that, what you get is you'll get a, if you turn that line, the position vector, into a unit vector, and you dot it with a force vector, you'll get the magnitude of the force times the magnitude of the unit vector, which is 1. So that'll just be the magnitude of the force times the cosine of the angle in between, which is the projection. Okay, that's what you would want in an engineering type application. Okay, so that's how that works. Okay, so the bottom line here is to get a projection of a force onto a line, you take the dot product of the force and the unit vector for the line. Now, the reason that we do this in engineering is we often want to know what that projection is, because we often have angled forces acting on a given line. And, excuse me, I'm going to shut the door here. All right, so what the projection of a force onto a line is, if the line is some sort of structural member, which it usually is, that projection of the force onto the line is called an axial force. And that's, if it stretches, it's positive, and that's tension. And if it compresses, it's negative, and that's compression, okay? So what we would have then would be, when you do this dot product of this particular example here, if you take the dot product of that force onto that line, what you're going to get in this case will be the compression that the force causes in that structural member that goes from B to A. And then you could, from force, you can calculate stress, and then you can look at the material you made BA out of and see what can handle in compressive stress, how strong it is. Okay. So that's why we're doing this. We can't analyze every possible angled force on a material. So what we do is we break up the forces into axial forces, either tension or compression, and then the force normal to that, which is called shear. And we can then talk about compressive or tensile strengths of materials and shear strengths of materials. That's why we're doing this, okay?
Does tension and compression just differ by negative?
Yes, tension and compression are just different signs. And what tension and compression do is they stretch the atomic bonds or compress them. Think of the bonds being like springs. what shear does is it slides one plane of atoms across another. All right? So that's why we're doing this. All right, so let's say we've got this set up here on 210. So we've got that force that goes from B to C. We've got that member AB. Force is what, 300 newtons. We've got an unknown angle in there. Why don't you start by getting the coordinates of A, B, and C. Okay. That's on 210. This is another thing that's kind of, we want you to know these projections. So again, I've got everything laid out in steps, step by step. So step number one there, of course, is get the coordinates. Then you're going to want to find the force. The force vector I have in front of you there again. So you want to read those dimensions in the different directions, okay, and get those written down. Okay. So I got A is 0, 0, 0, of course, that's the origin. B is 4, negative 3, 5, and C is 0, 0, 7. Are we okay with that? With those coordinates? Everybody getting okay at reading those dimensions? Questions on any of that? Just watch your signs on them. You bust a sign that carries all the way through and cause problems. So, okay. Good. All right. All right. So what do we do next? Now we find FBC. Okay, and there are the steps. You find the position vector from B to C. Remember, take RC minus RB. Then you find the magnitude of RBC, find the unit vector, and then find the force vector by multiplying up by the magnitude of the force. So why don't you fill those steps in? Got a couple of those answers in there just so you can kind of see how you're doing down the way. Do the subtraction on the vectors first and get the position vector. Find its magnitude, divide it out, and scale it up by the magnitude of the force. So from B to C ought to be -3, -4, 3, 2. Y'all got that? Okay. Next thing to do is to find the magnitude of that position vector. Theorem of Pythagoras. How to do that. You got questions, you know, let me know, or ask somebody or whatever. No, it's a step. So what you gotta do is it's
yeah, the magnitude goes right there. However we see it. No, just forward about
okay, magnitude ought to be about 5.385.
Is it because it's pointed that way?
No, the negative is because you're going RT minus RT. Negative is the arithmetic, you know, this is subtraction.
Okay. And it goes there too, just because.
Well, yeah, I'm saying RC minus RT, so I'm putting negative out.
Okay, that makes sense.
Yeah, that's 7 over here. That's 7.
That's true.
So square root of sum of the squares gets you 5.385 or thereabouts. And divide through by that. And you should get the unit vector.
That's the force, which is 300 times.
Then once you got that, you scale the unit vector up by the magnitude of FBC, and that gets you a force vector. So basically what you're doing there is you're finding that position vector, in this case from B to C, and you're taking the length of that vector out. And that's how you turn it into a unit vector. use the theorem of Pythagoras to find the length of that line, and you divide through by that length, then you get a unit vector. And what you got there is a vector that has the right proportions there. The point from A to B, or from B to C. Yeah, from B to C. And you scale that unit vector up by the, 300? I think it is. And you'll get a force vector. Okay. Okay, so that gets you the force from B to C. Now the next thing to do, if you've got that all right, is everybody doing okay with that stuff? Okay. Want to do something similar to the line, okay? Now notice I'm going RVA on the line. I have some reasons for doing that. That's how I did it. So the next thing to do is to get a unit vector from B to A. Now that isn't a force vector, it's just a unit direction vector. So once you, if you're good on that force vector, find the unit direction vector from B to A, okay? And let's all do it from B to A. Very similar process. You just don't take it as far. You don't scale the unit vector up, just leave it as a unit vector. So that length of that line from B to A is 7.07, I think. Now the one thing, you get tested on this stuff, of course. The one thing I want to emphasize with you is show your work when you're doing those tests, okay? You drop a negative, it just blows everything up. That's what it does. If if you're doing a subtraction of two vectors and you just happen to drop a negative, it's really hard to track it back and see what happened. So you got to show me what happened. If I see on your paper you dropped a negative, I take a point off. But if I get this answer and I can't tell where it came from, and it's midnight and I don't have 20 minutes to go try every possible combination to figure out where it came from, and I'm grading them, I grade a lot of these things. So, your job is to cover yourself, all right? Show me what you're doing. That's part of your job when you take a test. Don't make me figure it out. So just show your work, drop a negative, no big deal, take a point off. Don't show your work. This answer just comes out of the blue and I got no idea where it came from. That's a problem. Okay, just keep that in mind. Yeah. That's what the dot product is. To do a dot product, they call the X.
Right. Without the dot product.
Well, it depends. We want to find the projection first. Oh, we'll get here, okay? You're on the next page. Yeah, we'll get. All right, so we good? Okay, now, Why did we use the unit vector from B to A instead of the unit vector from A to B? Why did I do UBA instead of UAB? Yeah, what I figured here, I looked at that, you know, and I try and keep this stuff kind of visual. See, when I'm going from B to A, I'm getting that. It's going from B to A. See, that's the direction that projection's going. I looked ahead and I saw that. So instead of using UAB, I use UBA. Okay. Now what that means is when I do this dot product, I should get a positive answer because I picked the proper direction. Now, had I used UAB, what do you suppose I would get for an answer? I'd get a negative answer. So it's no big deal. If I don't, you know, if I used UAB, it wouldn't be any big deal at all. I just get a negative of what we're going to get. That's all. But all the same, I looked at ahead and went, okay, that's going from B to A, so I'll use UBA. That's what I thought they were going to do. Okay. All right. So now we go on the next page. These things take a little bit there. So find the dot product, okay? Now, dot products aren't that hard to calculate. You just find the like components and multiply them together. That's really all you got to do. Then when you've got them all, you add them up. Now that notation I've got there is FBC parallel to BA. That's what I mean by that subscript there. I've never seen a real official notation for that, so that's what I came up with. It's really, I might think of F compression might be another way to express it because BA is getting compressed. All right, y'all getting about 118 for the projection, thereabouts? Now, how do you get the magnitude of the compression in that member from B to A? What do you do with 126.70.9 and negative 78.8? How do you get the magnitude out of that? I'm tricking you, I'm kind of just add them up, yeah. Okay, I'm sorry, but yeah, I did that on purpose because people do that so often. I want to just call it out. You got the magnitude right there. You just add the numbers up. That's all you got to do, okay? So keep that in mind. Sometimes people make this kind of harder than it is, and they kind of get themselves in a little trouble. So all you do is just add the numbers up because a dot product is a scalar by definition. Those aren't I, J, and K components. They're numbers that you add up to get the 118. Okay, So all we're doing there, we're just taking the like components, multiplying them together, and we add them up. That's it. We good with that? Doing all right? Now I got that little question down there that I think we already answered. You know, if we would have used UAB instead of UBA, all that would have happened was we would have gotten negative 118.1. No big deal, okay? Doesn't make any difference. So, you know, so what? Just turn it around. If you pick the wrong direction for the unit vector, it's not a big issue at all. You don't have to redo it or anything like that. Just realize it goes the opposite direction you assumed. That's all. Well, no, does that little rubber thing on the top, is that pushed out? Or it should be. Oh, it wasn't. Okay. Yeah, that's the purpose of that thing. All right. So there we go. And then the other thing we can do here is find the angle between the two vectors. Oh, whoops. So I'm going to do a couple other things here. So this you might need some blank paper for this because I've kind of gone a little further with this than I did when I originally made it. So what if I want to find that force as a vector now? How would I make that into a vector? I got the magnitude as 118.1 or 118, whatever you want to call it. How would I make that into a vector? What's the force vector? I want it like an IJK vector. So what do I do with that force magnitude to make it into the vector that goes from B to A? Because that's what it is. What you going to do with that? Again. No, I'll do this. Yeah. What are you going to do? You got the magnitude. What do you do with a magnitude if you want a force vector? Yeah, unit direction vector. Do we get the unit direction vector?
Yes.
Yeah, we do. So just multiply it through. Take the 118 times the unit direction vector. Okay, that's what you do to express that as a vector. So the unit vector for this projection is from A to B. It's the UA, or excuse me, from B to A. It's the UVA. See? Okay, so you could get a vector if you want, just because you've got both already. You've got the magnitude and you got the unit vector. Multiply them together. Now, see, had we gone UAB, our magnitude would have been negative 118. And our UAB would be the negative of UBA. So you'll multiply two negatives together and it'll just come out, you know, the right way. So if you pick the wrong direction for the unit vector, it'll all come out in the wash. You just get two negatives in there, it'll all just come out. Okay. So what we just found there is the compression in that from B to A. So we've got the magnitude of the compression is 118.1. And if we want it in vector form, we've got it too. So again, if you are designing that strut that goes from B to A, you'd look at the area of it, use that and the force and come up with a stress. And then you'd look at the material that you made it out of and see what sort of compressive stress it could handle. We'll get into that a little bit in strength materials. Okay. All right. So we good with that? All right, now, the two things we want to design something are either the tension or compression, one or the other, and then the shear, okay? And as I've mentioned, the shear is normal to the tension or compression. So notice the sketch there, that vector relationship. The compression and shear are two components of the total force. Okay? And they all make a right triangle there. So notice that the compression is perpendicular to the shear. The compression and shear are components of the total. So F compression plus F shear, if they're added as vectors, will get you the total. Okay? So if you've got the total vector and you've got the compressive vector, you can find the shear vector if you want. So using this dot product, you can find the tension or compression directly, then you can back into what the shear is also if you want. And that would get you enough information to design that thing for this particular case, because you'd have both the compression and the shear in this case, and then given that, you could design it, see. Okay, so we go ahead and do that. If we want to find the shear in this thing too, we go ahead and find it. And there's a couple different ways to do it. So the important relationship there is there's a right angle between the compression and the shear. And also that in a vector sense, F compression plus F shear is equal to the total original force, FBC. All right. So if I want to find the vector for shear, what I do there is I take the original FBC, I subtract off the compressive vector, and I'll get the shear vector. So that gets me the shear vector. If I want the shear scalar, I can take that shear vector and take the square root of the sum of the squares and get the magnitude of the shear. So if I'm designing this thing, I've got a compressive force of 118 newtons and a shear force of 276 newtons. That's what it looks like here. So that's the information I'd use to design it. Okay. Any questions on that? You doing all right with that? Right. Now that's one way to do it. Now often you want to know the magnitudes, and you can get to the magnitudes more quickly, you know, if you want. Because you got the total and you got one of the components, so you can back into what the other component is pretty quick if you want. So we good on that? Looks like we're pretty good, eh? We're good. So if you just want to find the magnitude, what you can do is just use the Theorem of Pythagoras. FBC is the hypotenuse, and the compression and shear are the two legs of the right triangle, as I was just showing you. So you can solve it for the shear. It's FBC squared minus F compression squared. So that's another way. If all you need is a magnitude, that's the quick way to get to it.
BC with the hypotenuse?
Yes, that's that original force vector, that we started with.
Yeah.
And then the compression and shear are just components of it. And BC was 300, and then the compression was 118. Now you subtract here because you're solving for one of the components. You're not solving for the hypotenuse, you're solving for one of the two components. So subtract in the radical there. Okay. Questions on that? Okay, so that's two ways to get to the shear. Shear vector is, a fair amount more work. Shear magnitude, you can get it just doing this real quick, okay? All right, so that's a kind of a start on these 3D vector forces. So what we've got there for these 3D things is finding a force when you got the magnitude and the angles of the vector, finding the force when you've got the two coordinates of the line of the force and a magnitude, and then we just did projections, which get us to axial forces, either compression or tension, and then shear if you want. Okay. All right. Oops. All right, now let's kind of get to some of the basics that we'll do in statics. We'll kind of take a break from 3D here for just a little while, but then we'll get back to it. But let's just look at some basic statics if we're good on this dot product stuff. So we good? Okay. And then one other thing I'd mention is you've got the formula for dot product right on the formula sheet if you ever need it. It's right there. It's on the bottom left, I think, is where it is. So keep in mind that you've got that whenever you need it. So let's have a look at just some basic equilibrium here. So this is on 240. Now what we have is that basic equation by Newton that F equals ma. Now if A is 0, what that means is the sum of forces is 0. Okay? The most common case when A is 0 is when you have no motion at all, which is 90-some% of the time. That's what you use for statics. You do have a special case of moving at a constant velocity and having no acceleration also. That also is statics. But normally we think of statics as being not moving at all. Okay, that's where the word comes from. So just a couple examples here. So the basics of it are pretty straight up. I mean, if all those objects below are in equilibrium, you can solve for unknown forces knowing that. So if I have a ball or something and I'm pushing on it to the right with 40 pounds, and I know that it's in equilibrium, I can solve for F1. It's 40 pounds going the other direction. If I've got that ball and I've got 40 pounds to the right and 10 pounds to the left that I know, F2 then would be 30, because 30 plus 10 to the left equals the 40 to the right. And if the weight of this bridge is 6 tons, I know that the weight pushing on the footings And from the footings to the bridge would be 6 tons also. Now I might have to look and, see what those two forces are. They might be 3 tons and 3 tons if the bridge is symmetrical. If it's not, they might be slightly different, but I know they're going to add up to be 6. Okay. So there's a process to use this. Now, what we do with this stuff is there's a design process. And the idea here when you're doing design is to figure out all of the forces that act on an object. Okay? So what you do is you make assumptions as to what the loads are. In this case, the load would be the weight of the bridge. For this building, the loads were the weight of the structure. That's called the dead load, the weight of the furniture and the people and the vending machines and the equipment and all that. And that's called live load because it can move around. And then there's a snow load on the roof, and there's a wind load on the side of the structure. And we hope it doesn't happen anytime soon, but there might be an earthquake load on this building at some point, et cetera, okay? So when you're taking these classes at the beginning, they tell you what the loads are, what the forces applied to the objects are. They just show it to you. What you're going to be working at is finding the reactions on the supports, and that's what we use statics for. We know what the loads are. We want to figure out what those red forces are on the footings that support the bridge there and there, okay? So that's what we use statics to do, to solve for those unknown support forces, and they're called reactions. Okay. Once we have the loads and the reactions, then we can find the total forces on the object, then we can figure out the stresses on the object, and then we can design it so it'll withstand the stresses. That's kind of the sequence here. Okay. So when you're taking a class in statics, they give you the applied loads, you find the reactions. Okay. Now that'll change when you start working. Okay. When you're taking the class, the challenge is finding the reactions. When you start working, the challenge will become figuring out what the applied loads are. How much wind load should I use? How much, et cetera, especially if you're in a kind of a wide open field like mechanical engineering. You're going to have to figure out, well, what are all the loads that could be on this front fork of the motorcycle, And you're going to spend a little bit of time trying to work that out. Whereas in class, you're just given those loads. Okay. All right, so to analyze the forces acting on objects, we draw up what we call a Freebody Diagram. And I really don't know where that name comes from. It seems a little odd to me.
I think it's because instead of thinking of the object as being held in place, you think of it as just having a bunch of forces inserted on it. No.
Is that where the free body comes from? Kind of an object in space? Okay.
Like you normally think of this calculator as just sitting on the table, but you could think of it as being pushed on by gravity and being pushed on by the table.
So you just drop the calculator and you got the two forces going both directions. Okay, I get it. I think of sometimes I just call them force diagrams too, but whatever. So, the official term is free body diagram. And so I just abbreviate that with FBD because, it's kind of a long series of words there. So what you do, you want to draw up these force diagrams of the objects so you can analyze them. So to do that, you decide what you want the body, which is the object, to be. You draw a boundary around it, and then you draw on the forces acting on the body. There's two kinds. There's contact forces, which are caused by physical contact. So in the case of a calculator sitting on the table, the contact forces are the reactive force of the table on the calculator. And there's also what are called body forces, which are caused by force fields. In the classes I teach, we got one force field, and that's gravity. But if you take physics or something like that, there's others. There's magnetism, there's some other force fields, okay? So, but generally for us, it's just gravity. It's the weight of the object. So you want to show all the forces acting on the object is what you want to do. All right, we've got some special types of forces here, but we're close enough where I don't think I'll start that. So why don't I give you a couple dot products problems to go through. Okay, how about 151 and one, no, how about some actual dot product ones? How about one, I don't have this page for some reason. Somebody got their book open, it'd be about page 5, I think, because I don't have, oh, there, I got 5. Hang on here, what's going on? Come on, page 4. Has anybody got page 4? It's on page 4. Thank you.
Page 4 is 161 and 162.
Okay, how about 162 and 163? Now, 163 is actually on page 4A, I think. 4B? Oh, okay. 4B? Oh, okay. So 162 is 4A then, eh? Okay. And those will be due Friday, I think, this coming Friday.
Had you also assigned 151?
Yeah, I gave you 2 others, right, for Friday? 151 and 153. Okay, so you got 4 of those due Friday. And that's the 6th. We'll go over them tomorrow, okay?